Module 2, Lecture B, Strings and Bytes. By the end of this lecture, you will be able to construct stir, bytes, and byte array objects from different source types using appropriate encodings. Explain how string representations produced by built-ins like stir and reaper differ and when to use each. And use built-in conversions to move between text and binary data without data loss in common scenarios. Building strings safely. From numbers and bytes. When you turn numbers or raw bytes into strings, you are choosing how abstract or concrete your data should be. Strings are human-readable text, while bytes are numeric sequences that represent characters using a specific encoding. For example, you might convert a numeric temperature reading from a sensor into a string for logging or display, or turn encoded bytes from a network packet into a username string for a user interface. In each case, you are transforming numeric data into a more meaningful, human-friendly form. Converting numbers to strings is about choosing how they are represented, such as deciding on decimal precision or local formatting. This choice is especially important in financial reports and dashboards, where clear communication is critical. Once a number is turned into a string, it stops being just a quantity and becomes a label or message that can be stored or sent through databases and APIs. Understanding this shift from numeric to textual form helps you make better decisions about precision and localization. When converting bytes to strings, you must choose the correct character encoding because each encoding maps bytes to characters differently. The same sequence of bytes can produce different text depending on the encoding, which is critical for software that processes things like email headers, web pages, or device logs. A log file may store messages as raw bytes, and your tool has to decode them with the right encoding to recover the original text. By treating bytes as numeric data until you explicitly decode them, you control how they are interpreted and reduce problems like garbled text or data corruption. Python code. From numbers and bytes. Demonstrate how to turn numbers into text so they can be logged in a readable way, and how to convert raw bytes into text by choosing explicit character encodings. Then compare the original numeric or byte data with the resulting human-friendly text forms to highlight the difference between machine-level representations and what people can easily understand. We define a temperature value in Fahrenheit and then create a formatted text version of it that rounds the number to 1 decimal place and adds the letter F. This uses a formatted string that lets us insert the rounded value directly into the text. We then output both the original numeric value and the formatted text. This shows how to turn a raw number into a clearer, more readable form for logging or display. We begin with a numeric sensor identifier, such as the number 42, which uniquely identifies a sensor. We then turn this number into a text label by joining the word sensor with the number, converted to a string. This creates a human-readable label that is easier to use in logs or displays. Finally, we output both the original number and the text label to highlight the difference between the raw numeric identifier and its descriptive text form. We define a short status message with the text OK, and then convert it into bytes using ASCII encoding. This encoding step turns the characters into their corresponding numeric byte values, which is useful when text must be transmitted or stored in byte form. Finally, we output the resulting bytes so we can see the numeric representation of the original text. We first convert a sequence of bytes into a string using ASCII encoding, so the raw data becomes human-readable text. This decoding step restores the original message from its byte form. We then print the decoded text to confirm that the conversion worked correctly and that the message is fully readable. This explanation shows that bytes are numeric values, while strings are readable characters. By printing the numeric value of the first byte in the status message, it reveals that byte data is stored as numbers. This contrasts with strings, which present the same data in a human-readable form. The key idea is that bytes represent the underlying numeric data, whereas strings are the interpreted text version of that data. This material explains how to turn numeric and byte data into readable text for logging and display. It shows how to format a temperature value as a string with 1 decimal place and how to convert a numeric sensor identifier into a descriptive label. It then demonstrates encoding a status message into bytes using ASCII and decoding it back to confirm the message is preserved. Finally, it points out the difference between bytes and strings by examining the numeric value of the first byte in the encoded message. Encoding defaults versus explicit. When working with text and binary data, relying on default encodings can cause problems, especially across different machines or regions. An encoding is the rule set that maps characters to bytes, and if you do not specify it, the system chooses one based on local settings that may not match your data. As a result, files created in one region, such as log files or database exports, may appear garbled or produce errors when read on a system using a different default encoding. To avoid these issues, you should always be explicit about which encoding your code uses. When working with text and bytes, always specify the character encoding you expect, preferably a widely supported one that handles many languages. This makes your intent clear to both the computer and future developers, and helps ensure consistent behavior across different systems. For example, a team processing international survey data should always define the encoding so the information can be reconstructed accurately wherever the code runs. Relying on default settings may appear to work on a developer's machine, but fail on a production server with different defaults, causing subtle data corruption that might only be discovered much later. Choosing an explicit, standardized text encoding is essential for building robust systems that remain reliable as technology changes. Older, region-specific encodings worked when data stayed local, but modern applications must handle many languages, emojis, and special symbols. By consistently using a standard encoding, you protect data integrity across platforms and over time, so the stored bytes always decode into the intended characters. This avoids problems caused by outdated or machine-specific default encodings and keeps your data meaningful and accessible in the long term. Python code: encoding defaults versus explicit. show how using the system's default text encoding can lead to different behavior on different machines or environments, and contrast this with explicitly choosing an encoding. Emphasize that relying on defaults can cause inconsistent or incorrect handling of text. Conclude by recommending that you always specify the encoding explicitly to ensure reliable and predictable results across all systems. We begin by importing the locale module so we can check the system's default text encoding settings. This module lets us see how the system is configured to handle character data. Knowing this is important because it helps ensure that our text is encoded and processed correctly. This is especially useful when running code on different machines or in different environments. The code first asks the system what text encoding it prefers by using the locale module. It then prints this default encoding so the user can see what the system is currently using. Knowing this default is important to make sure text is encoded and decoded correctly, especially when running the code on different systems that may use different encodings. We begin by creating a text string that contains many different kinds of characters, including accented letters, currency symbols, and non-Latin characters, so we can see how various encodings treat them. We then display this original text before doing any encoding or decoding. This initial printout serves as a reference point, making it easier to compare and observe any changes that occur when different encodings are applied. This code takes a piece of text and converts it into bytes using Python's default character encoding for the current system. It then prints the resulting bytes so you can see how the text is represented internally. Because the default encoding can vary between environments, this step emphasizes the need to know which encoding is being used. Understanding the encoding is important since it affects how text data is stored, processed, and transmitted. We explicitly encode the text sample using UTF-8, so it is converted into bytes with a standard that supports many characters, including accented and non-Latin ones. After encoding, we can print the bytes to see how the text appears in this byte form. Using explicit UTF-8 encoding is important because it keeps text handling consistent across different systems and environments. We take the bytes that were encoded using the system's default encoding and decode them back into readable text using that same encoding. This converts the raw byte data into the original text form. We then print the decoded text so we can see how it was reconstructed. This step is important to ensure the text is represented accurately, especially when different systems may use different encoding standards. The code takes bytes that were encoded with UTF-8 and decodes them back into text using the same UTF-8 encoding. This process accurately reconstructs the original text without data loss or corruption. After decoding, it prints the text to confirm it matches the original sample. This demonstrates that using an explicit encoding like UTF-8 makes text conversion reliable. This code prints a reminder to always specify the text encoding when opening files or converting text. Relying on default encodings can cause differences in how text is handled on different systems. By explicitly choosing an encoding, such as UTF-8, you make sure the text is processed consistently. This helps prevent errors and avoids corrupting your data. This script shows why it is important to specify text encoding explicitly in Python. It first checks the system's default encoding, which can differ between environments, then encodes a sample text with special characters using both that default and UTF-8. By comparing the resulting bytes and then decoding them back to text, it illustrates how using the wrong encoding can cause errors or incorrect characters. The main lesson is to always state the encoding you want, such as UTF-8, to keep text handling consistent and reliable across different systems. Readable string forms. When creating strings in a program, think about how they will be read by both humans and computers. The same characters may need to look different depending on whether they are user-facing labels, diagnostic logs, or data for another system. Decide whether the string is meant for people, your own code, or external tools, because this affects how explicit or compact it should be, and which characters must be clearly visible. Designing strings with their audience in mind helps ensure they are both readable and useful. When working with strings that may contain invisible or confusing characters, such as new lines or non-Latin symbols, you should construct and display them carefully. Simply joining these strings can make logs or outputs hard to read. Instead, use clear delimiters or convert control characters into descriptive forms so their presence is obvious. When rebuilding text from raw network data, choose character encodings that preserve the original symbols so monitoring tools can show an accurate and readable view of the data. When working with strings, you should shape them to fit their context and purpose. In configuration files, they need to be clear for the program and easy for an administrator to edit, which can involve handling special characters and line endings carefully. For user-facing messages, focus on clarity and natural language while hiding technical details. By constructing strings thoughtfully, you can present the same underlying text differently for debugging, logging, or user interfaces, keeping each version readable and appropriate for its audience. Python code, readable string forms. This material focuses on how to show string data in ways that are easy for humans to read and useful for debugging. It explains the difference between friendly display strings and more explicit debug representations. It also highlights how to reveal invisible characters and escaped forms using simple examples so you can clearly see what a string actually contains. Define a variable that stores a user's name as a text string, but it accidentally includes a new line character. To display this name in a human-friendly way, we create a template that uses placeholders to insert the value into a readable message. We also create a second template for debugging that shows the exact internal representation of the string, including escape sequences like the new line. This debugging view helps us see how the string is actually stored in memory and identify hidden characters. The first print statement shows a user-friendly label that includes the user's name, which contains a new line character, so the name appears on 2 lines. The next print statement is used for debugging and shows the exact internal representation of the name, including the new line escape sequence, so hidden characters become visible. Finally, an empty print call adds a blank line to separate this output and make it easier to read. The code creates a byte sequence that includes a tab character between the words hello and world, then converts this byte data into a normal text string using UTF-8 decoding. This decoding step ensures that any special characters are handled correctly. The resulting text string, when printed, shows the tab as spacing between the words, making the output easy to read. This demonstrates how to turn raw byte data into a human-readable text format. The code uses a representation function to print the text stored in bytes, so that special characters, like tabs, appear as visible escape sequences for easier debugging. This makes otherwise invisible characters clear to the programmer. After showing this debug information, it prints a blank line to separate it from later output and improve readability. This example defines a string that represents a typical Windows file path, using doubled backslashes so the backslash character is correctly stored in the string. It then prints the path in a normal, user-friendly way, as you might see it in a configuration file. After that, it prints the same path using a representation function that shows each backslash explicitly. This debug-style output makes it easier to spot any problems with how the path string is defined. This material explains how Python uses different string representations for normal display and for debugging. When a string contains special characters like newlines or tabs, the regular output shows them in a human-friendly way, such as splitting text across lines or spacing it out. The debug representation instead shows these characters as escape sequences, making hidden characters visible. The same idea applies to file paths, where normal output focuses on readability, while the debug view shows every backslash clearly. Overall, the key point is that Python balances readability and precision by using different string formats depending on the context. Bytes and buffers. Bytes from integer iterables. In Python, a bytes object is a sequence of small integers, each one representing a single byte. You can build it from any collection of integers, such as a list or a range, as long as every value is between 0 and 255. This is different from creating text strings, which first encode Unicode characters into bytes. With bytes, you work directly with numeric byte values, so they must all be valid byte-sized integers. This makes bytes a compact, immutable way to store and transmit numeric codes efficiently. Building bytes from a sequence of integers is useful for sending numeric data, such as sensor readings, as compact binary messages. Turning these integers into a bytes object gives you a stable, unchangeable format that works well for transmission or storage. When this bytes object is shown as a string, it usually reveals its binary nature with escape sequences or numeric codes instead of readable text. This difference between a user-friendly view and a more technical representation helps you either quickly understand the content or inspect the exact byte values, including any non-printable characters. When you build a bytes object from a sequence of integers, different string views of that object change how you understand the data. A simple string conversion may show a mix of readable characters and escape sequences, which helps you quickly see if the data is human-readable. For deeper debugging or validation, you need a more detailed representation that exposes the exact integer values or their escaped byte forms. Seeing bytes as sequences of integers and choosing the right representation lets you balance readability with precise control over the underlying binary data. Python code. Bytes from integer iterables. This section focuses on how to safely and clearly build bytes objects from sequences of integers. It compares using lists, ranges, and generators as sources for those integers, highlighting that each can produce the same bytes data in slightly different ways. It also shows how the same bytes object can appear differently depending on whether you use the normal string conversion or the representation used for debugging. Together, these ideas help you understand both how to construct bytes from integer iterables and how their string forms can vary. We create a list of small integers where each value represents an ASCII code for a letter or a space. These integers are then used to build a bytes object, which stores the corresponding characters in binary form. In this example, the numbers 72, 73, and 74 map to the letters H, I, and J. 32 represents a space, and 49, 50, and 51 represent the digits 1, 2, and 3. This setup illustrates how bytes can be constructed from an iterable of integer ASCII codes. We can create a bytes object by passing a list of small integers to the bytes constructor, where each integer represents an ASCII code for a character. The constructor then converts these integer codes directly into their corresponding byte values. This method is useful when we want to work efficiently with binary data or store text in a compact encoded form. We can create a bytes object by using a range of integers, such as from 65 up to but not including 68. Each integer in this range represents an ASCII code and is automatically converted into the corresponding byte. This approach is efficient because it generates a sequence of consecutive byte values without having to list each one manually. We create a generator that produces 3 numeric byte values. In this case, the numbers 88, 89, and 90, which are ASCII codes for characters. We then pass this generator to the bytes constructor to build a bytes object directly from those values. This method is memory efficient because it avoids storing an intermediate list, which is especially helpful when working with large datasets or data streams. We use the representation function to show the raw bytes object created from a list of integers. This view exposes escape sequences so we can see exactly how the bytes are arranged internally. It is especially helpful for debugging or any time you need to inspect the precise byte values, including characters that are not normally printable. We are taking a bytes object that was created from a list of integers and converting it into a more readable string form. This is done by passing the bytes object into a string conversion function. The resulting string is easier for users to read because it hides low-level details like escape sequences. This makes it better suited for general display than the raw bytes representation. In this example, we are looking at how a bytes object created from a range of integers is represented. We use the representation function to produce a string that shows escape sequences, so every byte value is explicit. This detailed view is helpful for debugging or whenever you need to inspect the exact contents of the bytes. Finally, we print this representation to the console to compare how bytes objects from different sources appear. This example shows how a bytes object can be built from values produced by a generator, where the generator yields numeric byte values and the bytes constructor turns them into a single bytes object. We then use the representation function to display the raw form of this bytes object. This raw view includes escape sequences and other details, making the byte content explicit and easier to inspect or debug. This example shows that each element in a bytes object is stored as an integer. By indexing into the bytes object, we access the first three elements, which are the integer values for the ASCII codes of the characters H, I, and J. When these values are printed, it demonstrates that bytes can be treated directly as integers. This behavior is useful when you need to perform numeric operations on byte data. This script shows how to build bytes objects in Python from different kinds of integer iterables and how their output differs. It first creates a bytes object from a list of integers that represent ASCII codes, then creates others using a range and a generator expression. When these bytes objects are displayed with the representation function, they show escape-style sequences, while using the regular string conversion produces a more readable form. The script also prints individual elements from a bytes object to emphasize that each item is stored as an integer. Overall, it demonstrates that bytes can be constructed from various iterable sources and that their internal integer values and display formats are closely related. Buffer mutability basics. When working with bytes and buffer types, the main difference is mutability. A bytes object is immutable, so once it is created, its contents cannot change, and any modification creates a new object. A byte array is mutable, which means you can change its contents directly without making a new one. This affects performance and how each type is used, with immutable bytes emphasizing stability and clarity, and mutable byte arrays emphasizing flexibility as raw data containers. When choosing how to represent buffer data, first decide whether it is mutable or immutable. Immutable bytes, such as those in network messages or cryptographic hashes, should be shown with precise, detailed representations so you can see the exact data structure. In contrast, a mutable byte array used as a temporary workspace should be treated as a work in progress. This reminds you that its contents are not final and should not be presented as a stable value to end users. In real applications, choosing between mutable and immutable buffers affects both how you process data and how you present it. For example, when working with camera image data, a mutable buffer lets you efficiently change bytes while applying filters and makes detailed technical views useful for debugging. After processing, converting the result to an immutable buffer creates a stable payload for saving or sending. At that stage, a more user-friendly, high-level representation is better for displaying or logging the data. Python code. Buffer mutability basics. This lesson shows the difference between immutable bytes and mutable byte array objects by making simple changes to a buffer. You demonstrate that bytes cannot be edited in place, so any change requires creating a new object. In contrast, a byte array allows in-place edits, meaning you can modify its contents directly without making a new buffer. You also compare how each type is printed, highlighting the distinct representations of immutable bytes and mutable byte array objects. We begin by creating an immutable bytes buffer, which is a fixed sequence of bytes that cannot be changed after it is created. In this example, we use the ASCII text hello to initialize the buffer. Making the buffer immutable ensures that the data stays constant and cannot be altered during its entire use. We then print the original bytes buffer to show its initial state before performing any further operations. To change a single byte in an immutable bytes object, you must create a new bytes object rather than editing the original. In this example, we replace the first byte with the byte that represents the letter Y. We do this by taking that new byte and concatenating it with a slice of the original bytes that starts from the second position. The result is a new bytes object that contains the updated sequence, which we can then display. We create a mutable byte array buffer from the ASCII text hello, so that its contents can be changed directly. Unlike an immutable bytes object, this byte array lets us modify the data in place. We then print its original state to show the initial content and highlight how byte arrays support in-place changes that bytes do not allow. We demonstrate how to modify a mutable byte array by changing one of its bytes directly. In this example, we update the first byte by assigning it a new value. To do this, we use a function that converts the character Y into its corresponding ASCII integer value. That integer is then stored in the first position of the buffer, replacing the original byte. Finally, we print the modified byte array to show the result of this in-place change. We first print the bytes in the new bytes object to show the result of our earlier change to the first byte. Then we print the contents of the mutable byte array, converting it to a bytes object, so the output format matches. Seeing that both outputs now show the same sequence of bytes confirms that the in-place modification of the byte array was successful and that it now visually matches the new bytes object. We use the built-in representation function to view the official string form of a bytes object, which is helpful for debugging because it reveals the exact byte sequence, including escape characters. We then apply the same function to a mutable byte array object to see its official representation as well. Comparing these outputs shows how Python represents these two types of buffers differently, even when they contain the same visible byte data. This script illustrates the difference between immutable bytes and mutable byte arrays in Python using the text hello. A bytes object cannot be changed directly, so to replace the first character with Y, the script creates a new bytes object that becomes yellow. In contrast, a byte array made from the same text can be modified in place, so the first character is directly changed to Y, also producing yellow. Both forms now contain the same sequence. And the script then uses the representation function to show how the bytes and byte array types are displayed differently in Python. Binary literal basics. When working with bytes and other binary data, it is important to understand how their values are shown as text, especially when conversions to strings happen automatically. A binary literal is a human-readable way to write bits or bytes, usually with a prefix that indicates base 2 followed by zeros and ones. This format is convenient because it clearly shows the bit pattern, but it is still just text that the language runtime must interpret. Functions that prioritize precision often display binary values in a form that looks like a literal, so you can reconstruct the exact original value from the text representation. Binary data can be shown in different formats depending on the situation. For quick, interactive use, a compact and readable form like hexadecimal is often used to convey values efficiently. For debugging or recreating objects, a more literal representation that mimics binary syntax with prefixes and escape sequences is preferred. This detailed style is important when verifying network packet headers or comparing cryptographic keys byte by byte. Understanding these options helps you choose the most appropriate representation for your task. When working with binary data, choose how you represent it based on the situation. For end users, use a clear, descriptive format that emphasizes what the data means, such as identifying it as an image or audio. For development or security analysis, use a precise, literal format that can be used directly in code and avoids ambiguity. Switching deliberately between human-readable and exact binary forms helps you keep both clarity and accuracy. Python code. Binary literal basics. This material explains how Python's binary literals are used to represent exact bit patterns in a value. It contrasts the user-friendly string form of a binary value with the more precise representation form that shows its exact structure. Finally, it demonstrates how you can reconstruct the original values from these literal-style representations, confirming that the bit patterns are preserved accurately. In Python, you can define a small integer using a binary literal, which is written with a leading 0b, to indicate that the number is in base 2. This lets you specify the exact pattern of bits, such as the sequence 110011010, and have Python convert it to the corresponding integer value. Working this way is useful when you need precise control over how numbers are represented and manipulated at the bit level. We first show the integer value that was created from a binary literal, which reveals the decimal form of that binary number. Then we use the built-in function that returns the binary representation of an integer, displaying it as a string in binary literal style. Together, these steps demonstrate how Python can easily move between decimal and binary representations of the same numeric value. In this example, we first define an integer using a binary literal. Then, place that integer in a list and pass it to the bytes function. The bytes function converts the list into a sequence of bytes, which is a standard way to represent binary data in Python. This byte representation is important because many operations, such as file input and output or network communication, require data to be in byte form rather than as plain integers or other types. We first show a user-friendly view of a bytes object, which is easier to read but hides the low-level binary details. Then we switch to a developer-focused view that reveals the precise binary literal form of the data. This more detailed representation helps developers see the exact structure and content of the bytes object. Together, these two views balance readability for general users with accuracy and detail for developers. We use a function from Python's abstract syntax tree module that safely evaluates strings containing literal expressions. This lets us turn a string back into a real Python object without risking the execution of arbitrary code. In this case, we apply it to rebuild a bytes object from its developer-style string representation. By doing so, we ensure the reconstructed bytes object is secure to create and exactly matches the original. We first rebuild a bytes object by using the abstract syntax tree module's literal evaluation function, which safely interprets the developer-style representation of the byte sequence. This process recreates the original bytes in a controlled way. We then directly compare the reconstructed bytes with the original sequence. If they match exactly, it confirms that the reconstruction preserved the data without any changes. This script shows how Python works with binary numbers and byte sequences. It defines an integer using a binary form, then prints it as a normal number and in binary using a built-in conversion function. The script then turns this integer into a bytes object and compares the simple, user-friendly display with the more detailed, developer-oriented representation. Finally, it rebuilds the bytes object using a literal evaluation function from the abstract syntax tree module and confirms it matches the original, demonstrating that Python can represent and handle binary data accurately and safely. Understanding STR and Reaper. Debugging with Reaper. When debugging text and binary data, the way you represent a value can be just as important as the value itself. A debugging-oriented view exposes the internal structure of the data, including escape sequences and non-printable bytes that a normal user-friendly display would hide. This kind of representation can reveal issues such as extra carriage return and new line characters or unexpected null bytes in a network message. Seeing these hidden details helps you understand how the text was encoded, transmitted, and decoded, and whether any corruption or formatting problems occurred. When working with text and binary data from files or systems that use different encodings, a detailed debugging view is essential. It shows the exact characters present, including decoding errors and hidden control characters, so you can spot issues that might confuse other tools. This kind of representation also lets you verify that each byte of binary data is converted to the correct character and exposes any out-of-range values. With this transparency, you can quickly identify problems such as wrong encoding assumptions or unexpected byte order marks in the conversion process. When converting between text and binary data, a detailed debugging view helps you spot subtle differences such as extra spaces or incorrect quotation marks. This is especially important when syncing data between applications or saving user input in a database. Careful inspection ensures that names, addresses, and special characters are preserved exactly. By focusing on precision, you can quickly detect where any data loss or unintended changes occur. Python code debugging with ret. Use the representation view of a string to debug issues caused by invisible characters. By comparing the normal, friendly string output with the more precise representation output for the same data, you can see hidden characters that do not appear in regular printing. This is especially helpful for finding unexpected bytes that show up after encoding and decoding operations. In practice, the representation view reveals exactly what is in the string, so you can locate and fix these hidden problems. We create a string that contains a new line, a tab, and a trailing space to show how these invisible characters affect printed output. The new line moves following text to a new line, and the tab inserts horizontal spacing. The trailing space is easy to miss, but can matter when debugging. This string then helps us compare normal printed output with the more explicit view given by the representation function, which reveals these hidden characters. we use the print function to show the contents of the message in a way that is easy for users to read. By default, this function converts the message into a normal text string, so it displays the text as it would usually appear. It does not emphasize special characters such as new lines or tabs. This makes the output clean, readable, and suitable for situations where the exact internal structure of the text is not important. Here we use the representation function to display the message variable, which is especially helpful for debugging. It shows escape sequences and other non-printable characters that the normal print function hides. While the regular print function focuses on a user-friendly display, the representation function gives a more exact view of the underlying data. This precise output makes it easier to detect hidden characters or problems in the string. We convert the message string into bytes using UTF-8 encoding, so the text can be handled in a binary form. This step is important when storing data or sending it over a network, where binary formats are typically required. By encoding the message, we create a byte representation that systems can process reliably. This helps maintain compatibility and preserves the original text across different platforms and environments. This line uses the default print function to show the byte representation of the message, but it only gives a simple view. When bytes are printed this way, you do not see their internal structure or any escape sequences. As a result, it is not very helpful for detailed debugging. It is mainly useful for a quick look at the data, but it does not reveal hidden details such as special characters or encoding information. In this example, we use the representation function to display the byte-level form of a message. This shows the exact byte values and any escape sequences that are present. It is especially helpful for debugging because it reveals the precise structure of the data. By using this approach, you can also spot hidden or non-printable characters that would not appear with a normal print statement. We convert the byte representation of our message back into a text string using UTF-8 decoding to check that nothing was lost or changed. This decoding step lets us verify that the original text and the decoded text match. By confirming that the round trip from text to bytes and back to text preserves the content, we ensure the integrity of the data. This makes it possible to accurately compare the original and decoded versions. We use the representation function to compare the original message with the message after it has been encoded and decoded. This function shows a detailed string version of each message, including escape sequences. By printing these detailed representations next to each other, we can visually check that the two messages match exactly. This confirms that no data was lost or changed during the round-trip process. This script shows how a representation function helps debug string problems by exposing invisible characters. It first prints a message in a normal, user-friendly way, where special characters like new lines and tabs are hidden. Then, it prints the same message using the representation function, so you can see the escape sequences. The script also encodes the message into bytes with UTF-8 and demonstrates that normal printing of bytes can hide details. While the representation function reveals the exact byte values and escape sequences. Finally, it decodes the bytes back to text and confirms that the original and decoded messages are identical. highlighting how useful the representation function is for inspecting hidden characters and byte structures. Lossless string round trips. Lossless string round trips mean that when text is converted to another form and then converted back, you get exactly the same text, character for character. This is important in programming when you encode something like a customer's name into bytes to send over a network, and then decode it on another system. Every detail, including accents and emojis, must be preserved so the name stays identical in all systems. The main goal is that no information is lost or changed during these conversions. To keep text conversions reliable, you must use the same encoding, such as UTF-8, both when turning text into bytes and when converting it back. If you mix different encodings or let the system guess in one direction, but specify another in the opposite direction, you can lose data or see incorrect characters. Treat the encoding as a strict agreement between whoever sends the text and whoever receives it, so every character stays unchanged throughout the process. In sensitive areas like legal, medical, and financial records, even a tiny change in text can cause serious problems, such as misidentifying people, misdirecting information, or breaking audits and compliance. Everyday tasks like syncing notes, exporting chats, or archiving social media also depend on text staying exactly the same, including punctuation and different writing systems. To protect this integrity, applications should be designed so that every conversion between text and binary data is deliberate, reversible, and preserves the original content across platforms and storage systems. Python code, lossless string round trips. We want to demonstrate how UTF-8 encoding and decoding can perform a lossless round trip for text. This means we encode a piece of text into bytes using UTF-8, then decode those bytes back to text, and confirm that the final text exactly matches the original. By comparing the original and decoded text, we show that the conversion did not change any characters. We also highlight that problems arise when you decode the same bytes using a different, mismatched encoding scheme, which can lead to incorrect or corrupted text. We begin by creating a text string that includes special characters, such as an accented letter and an emoji, which serves as the original data we want to process. We then display this text so we can clearly see its exact content before any encoding or decoding takes place. This initial printout is important because it gives us a reference point to check that later transformations do not alter or damage the original information. The text is converted into bytes using UTF-8 encoding, which turns the string into a sequence of bytes that computers can store or transmit. After this encoding step, the program prints the length of the resulting byte sequence. This length shows how much space the encoded text takes up and helps you understand how efficient the encoding is in terms of storage. We take the encoded bytes and decode them using UTF-8 to reverse the encoding process and turn the bytes back into a string. This step is essential for accurately reconstructing the original text. We then print the decoded string to confirm it matches the original. This shows that when the correct encoding scheme is used, the encoding and decoding process is lossless. We verify that encoding and then decoding text with UTF-8 does not change the original content. To do this, we compare the original text with the text produced after the round-trip conversion. If they match, the result is true, which confirms that the process is lossless. In other words, no data was altered or lost during encoding and decoding. The code decodes previously encoded bytes using the Latin 1 encoding, on purpose to show what happens when the wrong encoding is used. The incorrectly decoded result is stored and then printed. This example demonstrates that using a mismatched encoding can produce unexpected characters and corrupt the original text. This line checks whether text that has been decoded using the wrong character encoding, Latin 1, is the same as the original text. It compares the incorrectly decoded string to the correct version and prints whether they match. This illustrates that using an incorrect encoding can change the data and cause mismatches. It emphasizes why consistent and correct encoding and decoding are essential for accurate text representation. This script shows how UTF-8 encoding and decoding can preserve a string perfectly, even when it includes special characters and emojis. The text is first converted into bytes using UTF-8, then converted back into a string, and the result matches the original exactly, proving the process is lossless. When the same bytes are decoded using a different encoding, such as Latin 1, the resulting text is incorrect. This mismatch demonstrates why it is essential to use the same encoding for both converting text to bytes and converting bytes back to text, and highlights the problems that can occur when encodings do not match. Printing and formatting. When printing values for people to read, focus on a natural, clear, and visually pleasing format. Use tools that produce user-friendly text and hide technical details like escape sequences, so accents and punctuation appear as expected. This is especially important for things like welcome messages, customer names, or product descriptions. In these cases, prioritize readability and tone over how the data looks to the interpreter or debugger. When working with text and binary data for networks or file storage, you must balance human readability with accurate reconstruction of the data. A format that looks clean and easy to read may hide important details such as new lines or tabs, which are needed to recover the exact original content and distinguish boundaries. More explicit formats that show escape sequences can seem cluttered, but preserve every character and structural detail, making conversions between text and binary safer. Always decide whether your output is mainly for people to read or for systems that require every character to be preserved exactly. Choose how you format data based on its purpose. For user-facing output, such as messages in a web app, use simple, readable text and let the system handle encoding. For storage or transmission, focus on precise representation, making boundaries and special characters unambiguous, even if the result is less readable. This can involve using formats like hexadecimal or base 64 for binary data, or escaping special characters in logs. Keeping human-readable output separate from strict data conversion helps maintain both clarity for users and reliability for systems. Python code Printing and formatting. This material explains the difference between printing text in a way that is easy for humans to read and formatting it precisely for technical use. It shows how hidden characters, such as spaces or control symbols, can change how a string looks in a human-friendly view, compared with a detailed technical representation. It also connects these printing choices to the ability to safely convert text to bytes and back again without losing information. Overall, the focus is on understanding how display decisions affect both readability and reliable round-trip conversions between text and its byte form. We create a text variable that holds a greeting, followed by a special character that represents a new line, and then a welcome message. This new line character causes the text to break onto a second line when it is displayed. We then print a short label to indicate that the output is meant to be easy for people to read. And finally, we print the text variable so the greeting and welcome message appear on separate lines in a clear, readable format. We first print a message to indicate that the next output will use a debug style. Then we use the representation function to show the message. This representation function displays escape sequences inside the string, such as the new line character, instead of interpreting them. This makes it useful for debugging or any situation where you need the exact, unprocessed form of a string for reconstruction or logging. To prepare a text message for network transmission, we first convert the string into bytes so it can be sent safely and efficiently. We do this by encoding the text using UTF-8, a standard character encoding that supports many different characters. This encoding turns the readable text into a sequence of bytes, which can then be stored and transmitted. Finally, we can print these bytes to see how the encoded message looks in its transmission-ready form. We begin by printing a short message to explain that we are about to display text that has gone through a full conversion to bytes and back. Next, we decode the bytes into text using UTF-8 so the original message is accurately reconstructed. Finally, we print the restored message to verify that the round-trip conversion preserved the content without losing any information. This script shows the difference between a human-friendly and a technical view of text. It first prints a message with a new line, so it appears as a normal line break. Then, it uses a debug-style representation that reveals escape characters, making hidden formatting visible. Next, it encodes the message into bytes using UTF-8, so it can be safely sent over a network. Finally, it decodes those bytes back into text, confirming that the original message is fully restored and demonstrating a safe round trip between text and bytes. In this lecture, you learned to construct string, bytes, and byte array objects from different source types using appropriate encodings. Explain how string representations produced by built-ins like string and repr differ and when to use each. And use built-in conversions to move between text and binary data without data loss in common scenarios. In the next module, Module 3, we will go over collections and views.
Thank you for your attention. See you all in the next lecture.